Okay, so here's the good news, bad news of today. It's good news, bad news. Which one do you want first?
Bad news.
Bad news. Okay, the bad news is you have to listen to me talk for about the next hour and 10 minutes.
Oh, good news now.
Okay? Good news is you don't have any homework.
I'll take that any day.
Right.
So,
Let it go.
Courtney, are you good with that?
Yes.
It's a fair trade?
Start talking to Brookham.
Okay. So, I'll try and make it as entertaining as possible, but
I'm just kidding. I won't do that.
that's your trade-off. All right, so let's talk about the lab. So,
Say it. Just continue.
thanks. Thanks.
I put you guys on
I
recording.
love it when kids give me permission to teach. Go ahead and teach. Okay. Because that's what I need. I need.
All you got to do is watch the video again and listen for what he said. So.
I didn't say nothing.
Oh, I really no.
Yeah.
It is amazing what they pick. Basically, right? Anything you say. Yeah. So,
We're like their brothers.
they're brothers.
Yeah.
But
Stop
they-
talking.
Or more like a play-by-play color commentary.
Yeah.
Like you're watching a sporting event.
Very,
Bob Costas.
a very quiet, whispering
It's
commentary.
like the golf thing.
Yeah.
Well, Brookham's going with a driver. I don't know about
Oh, he's going for the phone. He ripped it off the wall.
Hey, Brookham has changed color. He's going with the blue. He's going with the blue. I say, yeah. All right.
That looks like a velocity time graph to me, Garrett. I don't know.
All right. So here's the big picture. Here was the track. Gravity yet again worked for us. It rolled up. It rolled down. Right? So, Rosie, did the cart accelerate?
Yes.
Yes. When?
All the way up the ramp and down the ramp
Okay. Why?
because it changed velocity,
Yes. And it also changed,
position.
yes, but it went up and it came back down, so it changed
Side, slope,
of the, rhymes with position time graph.
position, time graph.
Okay, the position time graph, okay? So the cart went up, the cart went down. It sped up, it slowed down. It changed direction, it stopped. Was the cart ever, Paige, at constant velocity?
No.
No. Why? Okay, I got time. It's a Monday morning. We'll let you think.
I'm trying to remember.
Okay, well, here's the deal. Okay, I think your headband might be a little bit too tight. You might need to loosen that up. Between the hair pulled back into a ponytail and the headband, it might be cutting off circulation. And it isn't Monday morning. Okay? Now, let me throw this out to you. Okay? I'm going to throw you a lifeline. Okay? Every motion that we're going to study is either one of two things. It's either constant velocity or it's accelerated motion. Okay? That's it. Those are the only two options that you have. Either something's at a constant velocity or it's accelerated. That's it. So if it was ever at constant velocity, how would that show up on your velocity time graph?
Just horizontal line.
Horizontal line. So Rosie just said that that thing was continuously accelerating. So if you look on your velocity time graph, which hopefully you have drawn,
Yes.
is your velocity time graph, is there ever a horizontal segment on your velocity time graph?
No.
No. So therefore, you know that it was always
Accelerating.
beautiful. Okay. Now, hopefully you realize that on the way up, your velocity vectors were getting smaller, okay? And on the way down, your velocity vectors were getting larger. Okay, so that's one of the things that you need to do. So anytime your velocity vectors are changing, okay, that means you're accelerating. So you have to figure out in which way you're accelerating. Now, because we haven't started dealing with circular motion yet, which we will, but here's what you want to look at. Your acceleration only is one of two options. It's either in the direction of motion, which is making you speed up, or your acceleration is in the opposite direction of motion, which is making you slow down. Okay? Those are the only two games in town. You know, it's like it's either with you or it's against you. Okay? There is nothing in between. So your acceleration vector, and if you think about this when you drive, it's true. Either you're speeding up and your velocity vectors are getting bigger, or you're slowing down and the velocity vectors are getting smaller, or you're at a constant velocity. Okay? That's it. Only two games in town. So, when this thing is going up, okay, and you're defining up as being positive, right? We could have defined up as being negative. We didn't. But we just made it positive. So here's the biggest thing that you need to understand with this lab. And this is why I wrote this lab the way that I did. Okay? That's why I did this. Is that you all intuitively understand that on the way up, the velocity is positive. Just go, okay, yeah, velocity is positive. Okay, good. And the acceleration is negative. You don't have a problem with that. That clicks. Okay? You can go, okay, yeah, wrap my head around that one. Brilliant, Mr. Burkamp. Now, here's what you all want to think. Going up isn't the problem. It's going down that's the problem. So, you're pretty good about realizing, okay, right? It's going to slow down. Negative acceleration. It's going to change direction. Velocity is going to go negative. Now, here's what I find. Is that you all want to think that, ooh, on the way down, everything is going to change sign. You're going to think that the velocity goes negative, and you think the acceleration is going to go positive. Okay? Because you want to associate speeding up with positive acceleration. Okay? In your heart of hearts, that's what you all want to think. Oh, it's speeding up. It has to have positive acceleration. And it's somewhat counterintuitive to realize that, ooh, this thing can speed up with negative acceleration. Because you all want to associate negative acceleration with slowing down, which does happen. Okay? And you all want to associate positive acceleration with speeding up. Again, that could happen. Okay? But when you look at something slowing down, and this is where you go to the golden rules. When something is slowing down, the velocity and the acceleration have to have opposite signs. And when it's speeding up, they have to have the exact same sign. That's it. There is no exceptions to that rule whatsoever. So this is why your velocity time graph looks like what, Daniel?
It's a
Straight sloping line like this.
Yeah,
okay?
definitely.
I've seen, no, you're not the only one. I have seen more jacked up velocity time graphs this morning. It was a cruel way to start a Monday morning. When I go over to lab and I say, this is what it's going to look like, Daniel,
yeah.
Pay attention. This is all you had to draw in your velocity time graph. I had waves, I had swooshes. No. It's this. Now, here's the problem. And I told you all, you have to take a leap of faith. Because you don't know what the velocity is, and you all are flipping out going, but Mr. Burkamp, I don't know what the velocity is. I'm not uptight about it. If I'm not uptight about it, you don't need to be uptight about it. Okay? You're just going to go like this. Now, let's say, what was somebody's total time for the trip?
4%.
Huh? 4.83? Huh?
4.03.
Oh, so let's call it 4 seconds. Okay, in round numbers, let's call it 4 seconds. So Elijah says his total time was like 4 seconds. So that means it's going to take 2 seconds going up, and it's going to take about 2 seconds coming back down. That puts you way out here at 4 seconds. Good? Brilliant. Fantastic. Now, so this is all you have to do for your velocity time graph. This is it. This is all you have to do. Okay? This is it. Do not make this difficult. Now, what you're ultimately after on page 2, on the application of the terrible triangle segment of this, you need to figure out what that initial velocity is, okay? And this is where we get clever and we do a little bit of simple algebra. And we realize that area is 1/2 base times height, okay? The area here represents what? Courtney? Displacement. And you know what that is. Go to the front of your lab and you calculate displacement. It is position final minus position initial. Should be a positive number. I'm guessing somewhere around maybe 0.8 meters. Okay, depending upon how far you push the ramp or the cart up the ramp, something around 0.8 meters. So you're going to know this. Now, the base here is going to be half your time. Okay, because that's how long it took to go up. So you're going to know this. The only thing you're not going to know is the height. So, if you do a little bit of simple algebra, we talked about on Friday, so you multiply by 2, you divide by b, boom, you get h. That's all you have to do. So, if let's say Elijah's displacement was 0.8 meters, so he would take 2 times 0.8 meters and then divide that by 2 seconds. That's all you have to do. There's the height of that triangle. Lovely. Got it. Grand. Okay? Now, the next thing you need to do is find the acceleration. And again, you have to look at the big picture. When I ask you to find the acceleration, basically, what am I asking you to find on this graph? I'm asking you to find the slope of the line. That's it. So you're going to know this point is 0 something, and you're going to know this point is so many seconds and 0. You're finding the slope of the line. And acceleration, and we'll talk more about this today, acceleration is velocity final minus velocity initial over time. On the way up, and this is the huge transition that you have to make. On the way up, okay, on the way up, Mr. Baker, what is my final velocity?
On the way up,
Yeah.
would be 0.
Now, what's the sign of my initial velocity?
Positive.
Positive. So if I take 0 minus a positive number, Abby, what do I get? I get a negative number. Is my time ever going to be negative? No. So on the way up, I'm going to have a negative change in velocity divided by a positive time. Check my math, but that's going to give me a negative acceleration, which matches with this. Okay? So that's the easy part. Now, on the way down, so you break this up into 2 different segments. Read, Dairy Queen. On the way down, what's my initial velocity?
0.
0. So on the way down, it's going to start at 0. Okay? So on the way down, V naught is going to be 0. Okay? That's my initial velocity on the way down. Now, read, what is the sign of my final velocity on the way down?
Is it negative?
It is negative. Okay? So on the way down, I'm going to have a negative number minus 0 divided by time, other read, which hits me what? A negative acceleration. Okay? Brilliant. Got it. Grand. On your experimental error, remember that's theoretical minus experimental over theoretical. So basically, I don't remember numbers. So basically, you're going to calculate that at theoretical acceleration using A equals G sine theta. So you're going to negative 9.8 meters per second squared times the sine of whatever that angle is. I'm guessing that should be less than 1. Okay? Generally, it's around 0.5, depending upon what your angle is. Okay? Now, on that last problem that I've given you with the ball thrown up in the air, and you all are horrible at reading instructions, so I'm going to point this out. At some point, I'm going to tell you to go back to that velocity time graph. This is for that last problem on the last page. And write down the velocities that you have on the velocity time graph. So go to your velocity time graph, look at that on that last one, and see if you've written down your velocities. If you haven't, you might want to correct that. Now, here's how you can check if that last problem is right. Here's the simplest way that you can check this. How high does the ball go on that last problem? 5 meters. Now, to give you a reference, this ceiling in this room is about 2.5 meters. Okay? So this ball, this thing isn't, going to be high enough where you can see Neil Armstrong's footprints on the moon or anything. Okay? It's only going to go up about 5 meters. So goes up about 5 meters, it'll come back down. So here's what you can do to see if you at least have a fighting shot at getting this thing right. Go to your velocity time graph on that last problem. Find the area of that triangle. What does the area of that triangle have to be? 5 meters. So if you multiply your velocity times your base and take half of that, and you get 5 meters, at least you have a fighting shot of getting it right. But if this area here that you find isn't 5 meters, there's no way that it's right. Okay? There's no way that it's right. Any other questions on that lab? On that one where you have to sketch them going up and going down, okay? I want 3 velocity vectors on the way up, and I want 3 acceleration vectors on the way up. I emphasize, clearly label them, okay? Do not draw random arrows and expect, oh, Bergkamp will know what I mean. No. 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 Okay? I'm not. Now, if you want me to figure out that you think these velocity vectors are changing, draw them so that I can clearly see that they're changing. If you want your acceleration vectors to stay the same, you better draw them where they're staying the same. If you want those acceleration vectors changing, I better clearly see that there's enough difference that I can see that those are changing. Okay? Lovely. Any questions? There's way too much KU stuff in this room for me to feel comfortable right now. All your fault. Your fault. Oh. Okay, you'll take one for the team. Okay, anything else? Going once, going twice. So, staple the graphs to the back. Give those handed in. Okay, so get out yonder big dog equation sheet. So now we're really going to start to use this to its full capacity. And I need to show them how to use it, what they mean, all this good stuff. So the very first equation up there underneath the mechanics section on the left-hand side is this equation right here. Vx equals Vx naught plus Ax t. All right? Now, hopefully you all aren't flipping out. You're going, oh, I know that equation. Courtney, what is that equation? Have you seen this before? Yes, you have. You just used it on the lab. It's just what?
This equals the final velocity, right?
Yes, exactly. Now, when you look at this, it's very daunting. You're going, wow, it's got these x's in it. What are the x's for? You've never talked about x. Now, the reason that we put the x's in here is because eventually we're going to be dealing, even tomorrow, with vertical and horizontal motion. So, the only reason that the x's are there is that it's kind of like the ads for Las Vegas. What happens in the x stays in the x, and what happens in the y stays in the y. So instead of rewriting this with, oh, Vy and Vy naught plus Ayt, they said, okay, here's what's going to happen in the x direction. So what happens in the x, that's just what this means. So in other words, if you have any horizontal motion at all, the only thing that you can deal with in using this equation is horizontal motion. If you have vertical motion, okay, which we'll deal with tomorrow, the only thing that changes, so like let's say for example, if I drop this ball, okay, and I know that it's going to have a certain acceleration, and I want to know what the final velocity is, and it's falling vertically, instead of x's, I would have y's. So that's the only reason that that's put in there is in terms of just an emphasis going, okay, you have to keep track of which direction that you're accelerating in. Is it in the x direction or is it in the y direction? Now, as we go through this, okay, and over the years, I see this more and more and more. And this is actually why if you talk to anybody that's a senior this year that happened to take my physics class last year as a junior, they killed the big dog, okay? Because how this used to happen was that I would give you a blank sheet of paper with the big dog up there at the top, and you could write down any equation that you wanted, okay? And you could use it on the test. But what I found is that the kids were just writing down every minute possible equation that could exist. They had pages and pages of equations, and then they would get to a particular problem, and they would flip out because they're trying to find one equation to work for every specific problem. And basically they couldn't see the forest for the trees because they were so inundated with trying to find a specific equation to work a specific problem that they lost track of what was actually happening in the problem. They spent more time looking for equations than they were trying to figure out the problem. So that's why I've gone to this method. So you're going to have all the equations there, but they're just going to be broad general equations. You have to figure out how to use those broad equations. So my thought being is that you're going to have a deeper understanding of what's going to happen in these problems because you can't write down every possible equation to solve every possible problem. So, as we go through this, and you will hear me say this again and again and again and again and again and again, the dumbest thing that you can do, literally, the dumbest thing that you can do is to read a problem, and the first thing that you think of is, oh, what equation am I going to use? Okay? Dumb. Dumb. Don't do that. When you read a problem, and every problem you're going to have is a story problem. Okay? That's what physics is. Physics is story problems. You know, a plane is taking off from a runway. A car is slowing down. Okay? A squirrel falls from the tree. Something. Okay? It isn't, oh, here's an equation, plug the numbers in. Okay? Some event is going to be happening. So, as you go through this, the first thing that you want to do is to get an idea, say, okay, what is the big picture? Is this thing slowing down or is this speeding up? Now, as we go through the assignments that you're going to have for the next 3 days, not tonight, we're starting tomorrow. These are all going to be about acceleration. So if something is accelerating, okay, that's going to be the key. If something is accelerating, when you look at this equation, x equals like velocity times time. If something is accelerating, do not, under any circumstances, use this equation. Okay? Under any circumstances, use this equation. This will not work if something is accelerating. Why won't this work if something is accelerating?
Doesn't take into account acceleration.
Well, beyond that. At the end of the day, if something's accelerating, what is changing? The velocity. Well, if your velocity is changing, it's like, what number do you put in here? Okay? If you look at your car, you're driving along, you start from rest, and you get up to 55 miles an hour, and you want to figure out what your distance is that you're traveling when you're going from 0 to 55. It's like, what number do you put in there? Do you put in 20? Do you put in 25? Maybe 50 miles an hour. If your velocity is always changing, you're trying to hit a moving target. You don't know which velocity to put in there. Now, if you hit 50 miles an hour, and I say, okay, hey, you know, I know Rosie is driving at 50 miles per hour, and I say, Rosie, how far are you going to drive in an hour? Rosie's going to say, 50 miles. Okay? Well, that's easy, Mr. Burkett. I'm driving at 50 miles an hour. Now, if Rosie is going from 0 to 50 miles an hour and speeding up, and I said, Rosie, how far would you go? And she goes, I don't know. Really can't use this equation. You got to give me more information. Okay? More what's going to be happening. You can't use this because the velocity is always changing. Okay. So, if you find yourself trying to take distance and divide it by time to get a velocity in this particular unit, odds are you're doing something wrong. Okay? Just saying. Now, here's the bigger picture of this. Here's the velocity time graph. And it doesn't make any difference what this velocity time graph is doing. It could be going like this. You could have a velocity time graph that goes like this. Okay? It doesn't make any difference. Because if you look at this equation, and this is one of those things you have to see the big picture. All this is kind of written a little bit differently, but all this is a slope-intercept equation. Okay, this is all this is. Because they have the AXT over here, okay, but basically it's the same. You all have the capacity to go, okay, well that isn't that big a deal, I can flip that around. So, what does the acceleration in terms of a velocity time graph represent? The slope, okay? So, that's the slope of the line. Doesn't make any difference what the slope is. That's just the slope of the line. What's t in terms of y equals mx plus b? Your x. That's what's going to go on your time, right? Go. All this is what's on the x-axis. What's vx naught? Yeah, that's your y-intercept. Where are you going to start? Are you going to start at 0? Are you going to start at a positive number? Or are you going to start at a negative number? That's all this is. And vx, this last vx is going to represent what? What did you say, Courtney? Yeah, your final velocity. Where are you going to end up? Are you going to end up here? Are you going to end up here? Are you going to end up here? Okay? So all of this is the slope-intercept formula. That's it. Don't flip out. Now, a lot of times you're going to solve this for different variables. So, if you want to solve this thing for acceleration, okay, and you have to start to be good, if you're not good at algebra, get good at algebra. So, if you want to solve this thing for acceleration, what would it look like? Danny, what would this equation look like solved for acceleration?
Velocity final minus velocity initial
Over
time.
time. Okay? So, this is the exact same equation that this is. It's just solved for acceleration. So, these are going to be the two forms of this equation you will use 90% of the time. Okay? Probably more like 95. 95% of the time when you're dealing with acceleration, this is going to be the form of it. Okay? And it's about a 50-50 split between these two. So, but here's how this is going to play out. And by the way, your big test over acceleration, which is going to be the first of the really big tests in this class, is a week from today. Okay? So plan accordingly. A week from today, next Monday, first really big, full-blown physics test. Huh?
Those other ones.
No. Those are just kind of the warm-ups to the big show. Yeah, that was like those are like the pre-game non-conference games or preseason non-conference games. Okay, this is the first like for real conference. You know. So, but remember, what you're going to have on the test is a laminated version of this equation sheet. That's what you're going to have. So, even though this isn't here, you have to realize, oh, here's a simple thing. Now, let me give you a word of advice. If you're a little bit dodgy on, really not so much good on my algebra skills, okay? If you really are questioning your algebra skills and you want to like memorize this, and then as soon as you get the test, you can write this down. Oh, this is also it's the same version of this, okay? And you really want to, that's fine. But what you're going to start with is this. And again, but if you view this from, and I realize this sounds like kind of a 60s hippie free love kind of thing, but if you view the problem from a holistic big picture thing, okay, everything's in harmony, these acceleration problems become a lot clearer to understand. Where you run into trouble, and I've done this, trust me, kids get wrapped up and going, oh, how are we going to solve this? And they don't step back and look at the big picture. So I'm going to give you a couple of examples with this, and you'll see how this deal will play out. So let's say that we have the carrot car, okay? And it's moving at, I don't know, 16 meters per second, right? And there's there's a little squirrel in the road, okay? And the guy's driving the carrot car, so, probably a vegetarian, he's driving the carrot car. And he certainly doesn't want to hit the squirrel that's in the road. So he's going to hit the brakes and he's going to stop. And he's going to stop in, I don't know, let's say 4 seconds, okay? Now, because these are word problems, a lot of times you're not specifically told what the final velocity is. They will not tell you, oh, the final velocity is 0. But if the car is going to stop, what's the final velocity going to be? 0. Okay? There you go. Now, a lot of times, though not always, a lot of times the object, whatever you're dealing with, is either going to start at 0, okay, like they'll say, okay, the car was at rest and it sped up. Or the car was moving and it slowed to a stop. So a lot of times, although not always, one of your velocities will be 0. Not always, but a lot of times your velocities will be 0. Now, let's not even talk about an equation. Let's not even talk about an equation. Okay? Don't even think about equations. Block equations will be wrong. What's the car going to do? Speed up or slow down? Sydney, what's the car going to do? Speed up or slow down? Does it have positive velocity? Yes? So if this car is going to slow down, right away, what do you know the sign of the acceleration has to be? Negative. So right away, before you even start down this road, look at this, go, okay, let's kind of analyze this. I got a positive velocity. I'm going to be stopping so he doesn't hit the squirrel. Nice guy. The only way that can happen is if he has negative acceleration. True? It's the only way it can happen. Oh, stop that. That good. Okay. Now, what I'm ultimately after is my acceleration. And at this point you're going, ooh, ooh, ooh. Now we can use an equation. No, no, no. Graber, since because of you I got a phone call. What's the velocity time graph going to look like for this?
It's going to be a straight line that starts. It's not going to start at 0, but it's going to.
Where's it going to start?
It's going to start at 6.
Okay, that was the most non-committal, no faith in my answer explanation I've ever heard in my entire life. Let's have a little bit more feeling. A little bit more confidence.
It's going to start at 16 meters per second.
Yeah?
Yeah.
And it's going to go to
0.
straight line, curved line.
Straight line.
Okay? And so you're saying it's going to start up here at 16 meters per second and go think like this. Beautiful? You sure? Perfect. Okay? That's it. That's all you have to do. Okay? That's all you have to do. Now, unless I specifically tell you differently, which is going to be very, very rare, unless I spiderweb or something. Unless I specifically tell you different, you always assume that you have uniform acceleration, which means that it's a straight sloping line. Okay? So, and it makes life easier. Okay? Because otherwise you get curved lines, then you're trying to find areas, and you have to have calculus. So, unless I explicitly tell you different, when you draw this velocity time graph, you draw this as a straight sloping line. And that, trust me, you want that to happen. You don't have to think, you don't have to have calculus to find the area of life is going to be green. Now, Graber, how long is it going to take to get to this point?
4 seconds.
4 seconds. Lovely. Okay? 4 seconds. Now, am I going to end up with a negative acceleration? Graber? Am I going to end up with a negative acceleration?
Yeah.
How do you know? And you're right, you are, but how do you know?
Because you have a positive velocity and something slowing down, so it's
There you go. I know I have to end up with negative acceleration. I have positive velocity, I'm slowing down, boom. So basically, one of 3 things, and if you think this through, you only have one of 3 things that can happen. If this car starts at 16 meters per second. If the car starts at 16 meters per second, okay, there's only 3 things that car can do. What are the 3 things? What's one of them? Hey,
The car can either slow down or wait.
you're on a roll.
Stop and then speed up. I missed what you said.
If this car is going at 16 meters per second, at some point later, let's say 1 second, what are the 3 options that could happen relative to 16 meters per second?
Oh, it could either be going at the same velocity, a slower velocity, or a fast velocity.
Yeah, one of 3 things is going to happen. Either this car is still going at 16 meters per second, which would mean the acceleration is what? 0. There is no acceleration. Or it is speeding up, or it is slowing down. So those are the only 3 games in town. And let me give you a hint, because we're studying the acceleration unit, which one do you think is not going to happen? The constant velocity. Okay? If we were constant velocity, we would call it the constant velocity test. It's not. It's the acceleration test. Guess what we're going to emphasize? Acceleration. So, which means with 16 meters per second, it's either going faster or it's going slower. And in this case, he doesn't want to hit the squirrel, so because he's driving the carrot car, so he's going to slow down. Okay? Now, basically, let's pretend that you're in a math class. Okay? Let's pretend that you're in a math class. Elijah, what are my x and y coordinates for this point?
16, 0. Or 0, 16.
Which one is it?
0, 16.
You sure?
Yes.
Okay. You should. So this is 0, 16. Okay? Good progress.
Good morning.
How are you?
Excellent. And yourself?
If I were any better, I'd be an administrator.
Absolutely. You know what you need? I've seen you doing angles and stuff here, right?
A little bit.
You need to ask Mr. West, what was the angle of knocking the ball out of the game?
You know, ironically, that was the first problem we worked this morning.
There we go.
It was. We studied his motion relative to that play. So, yeah.
Oh,
Okay. So it goes.
What's going on?
All right. So, Elijah, what's the coordinate of this one? 4, 0. Good? Got it? Now, if you're in math class, Rosie, what's the slope of this line? What would you do?
You take the y coordinates to go to the x coordinates.
You would. So, which one would you want to take? 0 minus 16 or 16 minus 0?
0 minus 16.
Okay? So we're going to take 0 minus 16 and divide that by 4 minus 0, and you're going to get what? -4. Now, if you're in a math class, you're done at this point. You had the 2 x and y coordinates, and the 2, you had both sets. You did change in y over change in x. Life is grand. Hey, move on. 10 out of 10, and give me the gold sticker. We're fantastic, right? Now, but because this has a physical meaning, Abby, what units do I end up with?
Meters per second squared.
Beautiful, with feeling and no hesitation. I like that. Okay? So -4, and with significant digits, I'm going to end up at -4 meters per second squared. Now, here's what you have to understand. And we've talked about this. But acceleration is the rate at which a velocity changes. Okay? That's what it is. It is not how fast you're going. It's the rate at which your velocity changes. Now, you're going, okay, brilliant. Everything makes sense. I've got a negative acceleration. I've got a positive velocity. Draper was right. She said, okay, I'm going to end up with a negative acceleration. Boom, I start at 16 meters per second. Lovely. Now, let's go to the equation. You're going, oh, right. So at this point, what we did, and Rosie just used math, but basically what she did is she used this. V minus V naught over time. And most of the time when I write this, I'm not going to put in the x's because everybody knows in this situation we're dealing with the x. So I'm just going to write this V minus V naught over time. If you're a real stickler, you can put x in there. Now, as you go through these problems, starting tomorrow, and tomorrow you will get the first real physics assignment, there's a certain procedure, what? Like you haven't had physics assignments?
We'll be like 3 weeks into school now.
Yeah, but this is the first real physics
Oh,
assignment.
okay.
The
That's
other
just like,
ones have kind of been like
just like
beat up.
week,
assignments.
4
Again,
weeks into
those
school.
are like non-conference games. Now we're into the big leagues. Okay?
Okay,
Okay, whatever.
So I gotta be on all the
All right.
great.
4 or 5, tomato, tomato, potato, tomato. Now, there's a certain sequence that you go through. Now, I cannot emphasize this enough, and Garrett will readily attest to this because Garrett's been my student before. I am not concerned just with the answer. The answer is important, don't get me wrong. Okay? The answer is important. But in an ideal world, okay, there would be 3 parts to every problem that you do. I would see the equation that you used, okay, which is like this. I'd say, oh, okay, A equals V minus V naught over time. Okay, I would see an equation. Then I would see the numbers substituted into that equation with the units, okay, with the units, just not numbers. Because if you come up to me and you go, man, Mr. Burkamp, I got an answer, but it's wrong, and I don't know what I'm doing wrong. And invariably, 99% of the time, when kids come up in that situation, I'm going to look at their paper, and I'm going to see like maybe 5 numbers written down without a single unit on any of the numbers. And then a miracle happens, and then you get like meters per second squared. And that's exactly what I will say to you. I will mockingly say to you, gee, 5 numbers, not a single unit on any of them, but yet a miracle happens and you get newtons or velocity or whatever it is. Okay? Bam. Okay? Bam. Let the units lead you to the promised land. The units, if you embrace this idea, are an integral part of how you do physics. I am more concerned, to be honest, I am more concerned with the process than I am the answer. And if you say, well, I love this one. I did it in my head. Really? Really? Staple that paper to your head and hand it in. Okay? True story. Or, I did it on my calculator. Brilliant. Staple that paper to your calculator, hand it in. And I'm not doing this to be cruel. I'm not. Okay? Again, I'm not doing this to be cruel. I'm not doing this to be a jerk. When I work out problems, okay? And again, I've worked physics problems longer than you guys have been alive. When I work physics problems, this is the exact procedure that I go through. It is a sequence. It is a way of thinking through this. If I thought that you all could do this and not show any work, it would make my life simpler. I wouldn't have to worry about looking through your work. Okay, I wouldn't have to worry about looking at the equation. I could like, okay, hey, Danny got 4. Okay, brilliant, boom, let's move on. Okay? Doesn't work that way. Literally, when I work out new problems, and I'm honest God, this is the honest God's truth. You can look at any problems that I work through. This is the exact process that I go through. And because it works, because it forces you to think it through. It is demonstrating that, okay, hey, this is what I have, this is what I'm going to try and find, this is how I'm going to get there. Then, here's my final answer. Okay, so do not get wrapped up in this mentality of saying, well, I got the right answer. I don't care. I honestly don't. Dumbest thing you can ever say to me is, I got the right answer. Stupid, 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 right? I'm more concerned about the process than I am about the answer. And if all I see is the answer, and there's no work, I promise you will not receive full credit. And again, don't go, well, I got the right answer. Don't care. Part of your grade is showing that work. Okay? Trust me. And I'm not doing this to be a jerk. I'm doing this because at the end, you will have a deeper understanding of it. You will be more successful at the end of the day. And if I didn't think you had to do that, I wouldn't worry about it. Okay? Brilliant. Good. So, here's my equation. A equals velocity final minus velocity initial over time. And then you would plug in the numbers and you would go, okay, final velocity, 0 minus 16 meters per second divided by 4 seconds. I'm going to get negative 4 meters per second squared. Boom. There we go. So in an ideal world, here's my 3 steps. Here's the equation. Here's my numbers with the units written on it. Boom, there's my answer. Now, let's go to the big picture. So what's on your equation sheet is this. Okay? So at this point, if we were to fill in these numbers, what would we put in for V9? Do not make this difficult. This problem that we just worked with. Why 16? Read. Why 16?
It's our initial.
That's my initial velocity. On my velocity time graph, I started up here at 16. That's my y-intercept. My acceleration was what? -4 meters per second squared. And then I've got some value of time. Okay? Now, here's the deal. So, this is my generic broad equation. I can use, once I figure this out, I can figure out what this velocity is at any point in time. Okay? I can pick any point. So, Riley, if I put in 0, what should I get as my velocity?
16 meters.
That's right, because I'm saying, okay, times 0, I'm going to 16. David, if I put in 4 seconds here, what should I get as my velocity?
Your ion?
Which would be what? So, if I take 4 times -4, I get
Maybe 16.
-16 plus 16 gets me?
0.
Don't make this difficult.
16.
-16 plus a positive 16.
0.
0. Okay?
Confidence.
Right?
Or
0.
period.
Okay? Because that's when this thing is going to come to a stop. Now, interesting thing happens. Okay? Interesting thing happens. Sydney, what if I put in a value of time greater than 4 seconds? I'm not worried about the number. If I put in any value of time greater than 4 seconds, what's the sign of that final velocity going to be? Negative, right? Which would mean what? At that point, we're doing what? Yeah, we've changed direction, okay? Now, be very careful, okay, and get out of your minds right now that positive velocity always means that you're going forward, and negative velocity always means that you're going backwards, okay? It's completely arbitrary. I could have started this graph at -16 meters per second and had that graph go up like that, and I could have made that forward direction be negative. So there is nothing magical whatsoever that positive velocity always means that you're going forward, and negative velocity means that you're going backwards. Okay, so block that out of your mind right now. Did I change direction? Yes. Okay? But that doesn't mean I'm necessarily going in reverse. Good so far. Good. Now, at this point, here's what we have. Here's what we have. I'm up here at 16 meters per second. The slope of this line is -4 meters per second squared, and that time is 4 seconds. Okay, so here's what we've got. 16, slope, 4 seconds, boom. Beautiful. Now, I want to know how far the car went in these 4 seconds. Okay? Basically, you know, how far away is the squirrel? Okay? How far away is the squirrel? That's what I'm asking. Now, I was going at 16 meters per second for 4 seconds. So here's the big question. Hey, to get this distance, could I take 16 times 4 to get my distance?
Yes.
Yes. Okay? So Hayden, with feeling, emphatically, no hesitation, and the hair even moved with it, which was impressive, added to the effect. Hayden says I can take 16 times 4, right? 16 times 4, anybody? 64?
64.
64. Close. Well, 16 times 2 is what? 32. So 2 more, 64. So, everybody cool that the car traveled 64 meters before it hit before it stopped. Are you all good with that? Raise your hand if you're good with that.
Great. Oh,
Because you have to divide it by 2.
None of you should be good with that. All of you should be emphatically shaking your heads going, no, Mr. Burkham, you already explained that we can't do that. Hayden, are you going 16 meters per second the entire
No, you're
time?
not.
No. What are you doing?
You're or accelerating.
Oh, did you seriously?
I caught it though. I caught it.
Oh god.
Oh, I'm going to need aspirin. Okay. And we have it on film. Go back and reference it. Okay. Why are you not going 16 meters per second the entire time? I'm giving you a chance to redeem yourself. Why are you not going 16 meters per second the entire time?
Because your velocity is decreasing.
Ah, I like that. It's changing, right? You're accelerating, right? He almost said the D word. He got himself, thank God. Because, look at it this way. If he's traveling 16 meters per second the entire time, he's not going to stop. Right? Rocky the squirrel is going to be in bad shape. Okay? Right? It's not going to end well for Rocky. So, Rocky and Bullwinkle.
He's never seen it. That was
Seriously?
my favorite cartoon.
Rocky and Bullwinkle?
The big moves, he sounds stupid.
It's on the Geico commercial.
Yeah, actually it is.
Yes!
Well, I'm
Mr. Bullwinkle?
Funny in Sherman.
They were in the movie with the
Oh, dear
Kells.
Lord. If I have time, I'll pull up a
Keenan.
YouTube video.
Both.
Okay. Rocky and Bullwinkle. Yeah, Bullwinkle's the most flexible. Okay. The Canadian Mountie? Yeah. Okay. Boris, the bad guy? Oh, Boris? All right. Anyway, so what Hayden and some of you, Riley, jumped in on the bandwagon, you all tried to use this. You all tried to take 16 meters per second times 4 seconds, and I blissfully led you astray and said, oh yeah, that's 64 meters. Okay? We even did the mental math. We were feeling good about ourselves. Wow, we did mental math. 16 times 4. Ah, we're on our game, right?
Staple it to
Brilliant.
your head and hand it in.
Now, there's just so many issues. Okay, so if you tried to do this, 16 meters per second for 4 seconds, okay? What would your velocity time graph look like to represent traveling 16 meters per second for 4 seconds? What would that look like?
Horizontal.
Okay? You got this action going, right? International sign for 16 meters per second for 4 seconds, right? And you're saying, hey, I've got a rectangle that's 16 meters per second high, is 4 seconds wide. The area of this would be 64 meters. Life would be grand. But is that matching with this? No! No! This is not a rectangle. It is a
Triangle.
triangle. Triangle. Now, Riley, since you jumped in on the rectangle train, okay?
I jumped off.
Well, but you were on it to begin with,
Load
okay?
off.
So let's get on the triangle train then, Riley.
Yes.
Now, for the lab that you just handed in, I've given you the height of the triangle, right?
Yes.
I've given you the,
Base.
could you find this area?
Yes.
And what would you use?
1/2 base.
Okay, now, I'm going to draw this so it's a little bit cleaner, a little bit bigger. So we're here at 16 meters per second. We're here at 4 seconds. So my base is 4 seconds. This is my height, right? And Riley said, now that he's on the triangle train, 1/2 base times height, right? So he's taking 1/2 my base, which is, in this case, 4 seconds, times 16 meters per second, right? And you would get what?
32 meters.
32 meters. Now, does it make sense that this answer, when he's slowing down, is less than when he was driving at a constant velocity of 16 meters per second? Yes. Okay? Because that area would be a lot bigger. Okay? Because if he was cruising along at 16 meters per second the entire time, that would be an entire rectangle. He's slowing down, so we have a triangle. Now, think about this. So pretend that this problem isn't here. Okay? This problem is gone. Okay? Problem is gone. I tell you that you slow down from 16 meters per second to 0. Okay? Now, let's even pretend that we don't have units on there. I'm going to give you two numbers, 16 and 0. Mr. Moon, what is the average of the two numbers of 16 and 0?
8.
8. You took 16 plus 0 and you got, and divided by 2 and you got 8. Right? So 16 plus 0 divided by 2, you get 8. That's your average of 16 and 0. Right? Now, think this through. Okay? Think this through. If he's starting at 16 meters per second and he's ending up at 0, what do you think his average velocity is? 8. Okay? So his average velocity, okay, put anything with a bar over it means average. So his average velocity, and because we're talking about velocity, we'll do this. So his average velocity is 8 meters per second. He was going faster than that half the time, right? And half the time he was going less than that. But on average, he was going 8 meters per second. Now, I want you to look at something. Okay? I want you to look at something. If I said, I'm going to draw a velocity time graph with a constant velocity of 8 meters per second for 4 seconds, what would the area of this be? 8 meters per second for 4 seconds. What would this area get me? 32 meters, right? So, here's what I want you to look at. If his average velocity is 8 meters per second. So what we're saying is that he's going to average 8 meters per second for 4 seconds, which is going to get you 32 meters. Okay? Or, you can come back here and say, well, if I find the area of this triangle, taking 16 going to 0 over 4 seconds, I also get 32 meters. Now, in the simplified version of what Brett Moon just did, okay, he said, okay, hey, fundamentally we found an average velocity. Now, you're always going to have two velocities, an initial velocity and a final velocity. So, Brett, what would be a generic way of saying, if I give you an initial velocity and a final velocity, how would you find the average of those two velocities?
Final minus initial. Initial minus final divided by 2.
Brett, I give you two velocities, 16 and 20, okay? You're going from 16 to 20, 20 to 16.
Initial plus final.
Divided by
2.
2, because you're finding an average of two values, right? You always add them together and divide by 2, right? If I want to find the average height of Reed and Elijah, what would I do? Add their heights together and divide by 2. So, now, what I'm about to write on the board is not on your equation sheet, okay? It's a handy-dandy little equation. Some people like to use it, but there's a broader idea that this comes from. So, the other thing that you can do to find distance traveled, okay, and x is always going to, on this sheet, x will always be a distance traveled. I'm going to write this in a couple different ways, but you end up with the same thing. One is that you do exactly what Brett just said. You take velocity final plus velocity initial, okay, and you divide by 2, and that's going to get you what? The average velocity. And then to get the distance traveled, you would take that average velocity and do what? Multiply that by what, Sydney? Oh, sure you do.
I didn't, like, everything that you just said is,
Okay, Sydney.
so let's.
So let's let that curly hair of yours catch some of this that just went over the top. Okay? All right, so sit up tall and straight so I have a bigger target to aim for. Okay? Now, Sydney. Okay? This car started at 16 meters per second. Right? Started at 16. The final velocity was 0. So let's just don't worry about anything else. I want you to find the average of two numbers, 16 and 0. What would you do? Beautiful. So when I take 16 plus 0 and divide by 2, I get what? 8. So what we're saying is on average, this car was going 8 meters per second. Good? If I had gone from 32 to 0, what would be my average velocity? 16. Okay? So you see where we're going with that part of it? Good. Now, so if I tell you, now pretend that nothing else is here, Sydney. Pretend that all of this is gone. I tell you that you run 8 meters per second, right, for 4 seconds. How far did you run?
Is it constant?
Yes. You're running at 8 meters per second for 4 seconds. Constant speed. 32 meters, right? So you took the average velocity and multiplied it by what? Beautiful. So this right here, this part gets me my average velocity. And then I'm going to multiply all of that by time. Okay? Got that? Brilliant. So this is how some people like to think about this. Now, I'm going to do this a little bit different. Okay, just a little bit different. I can also rewrite this as this. V plus V naught times time. Do I get the exact same result? Yes? 16 plus 0, half of that gets me 8. 8 times 4 gets me 32. Good with that. Okay? So all we're doing is getting the average velocity. Good so far. Okay? Now, here's the other way that you can look at this. Okay? And this is a little bit more voodoo, and I'm going to end up in the exact same equation, so don't flip out. So let's say you have a velocity time graph that looks like this. Great. Am I speeding up or slowing down? Right. I'm going away from 0 meters per second. So this is going to be V, this is going to be V naught. Now, this is going to be some amount of time. Now, this is where this goes full circle. If I found this area, what would that represent? Displacement. Now, if you look at this, this has two distinct parts to it. It has a rectangle and it has a triangle, right? So, if it's just a rectangle, read, if it's just this rectangle, what would I multiply together to find this area?
Average velocity?
No. If all you have is just this rectangle, you don't see anything up above it,
Okay.
would you just take this velocity times time?
Yes.
Yes. So this area right here is my initial velocity times time. Okay? Oh, that's actually V naught. That's V. Okay? So this would be V naught times time. My initial velocity times time. That would get me this area. Good so far. Now, this area up here looks like a triangle. 1/2 base times 1/2 base times height. 1/2 my base, which is time. My height, now, the height gets a little bit tricky. If this is V and this is V naught, how would you get this height? What would you subtract?
V minus V.
V minus V naught. So that's going to be V minus V naught. Now, I'm going to do a little bit of weird algebra. It's nothing really weird. I'm going to take this and I'm going to distribute the 1/2 T. So I'm going to get 1/2 T times V minus 1/2 T times V naught. Okay? Good so far. Now, if I want to find this entire area, V naught T is this area. This is going to be this area. How would I find the total area? Add those together. Oh! See what happens. So I've got V naught t plus 1/2 Vt minus 1/2 V naught t, right? Can I combine some terms? If I take V naught t minus 1/2 V naught t, I get what? So I get 1/2 Vt plus 1/2 V naught t, right? Just combining some terms. Now, oddly enough, what I could do, wait for it, I could factor out a 1/2 at a time. I would get 1/2 V plus V naught times time. And oddly enough, I could write this as V plus V naught over 2 times time. And this part here just gets me what? Average velocity, and I'm going to multiply that by my time. So there's a whole bunch of different ways that you can arrive at this. You can look at it as average velocity times time. You can look at it as the sum of the areas underneath the velocity time graph. Okay? That's making a difference. Now, Rosie, are we good?
Yeah.
Okay, you're kind of going, whoa. Okay? I know it's a lot to take in on a Monday morning. You can handle it. Okay? Oh, seriously.
It's fine. It's
Okay.
still going.
Yeah, c'est bon.
Now, here's my question. Now, I want you to think this through. Okay? I want you to think this through. Riley. You run at 16 meters per second for 4 seconds. How far do you go?
64.
64 meters. Now, could I use this equation even with constant velocity? Does this equation work even with constant velocity?
Yes.
Why, Riley?
Because when you add 2 of the same number and then divide by 2, you get back to the same number.
And then you're taking that same number and multiplying it by
Time.
time. So, the beauty of this equation is that this equation here even works under constant velocity. This is like a Swiss Army knife of equations. You go, oh, well, that's kind of clever. So if I said Riley's running at 16 meters per second, okay, so guess what? If he takes 16 meters per second and adds that to 16 meters per second, and divide that by 2 and multiply that by 4 seconds, oddly enough, he's going to end up at... So this even works with constant velocity or accelerated motion. Doesn't make any difference. It's the exact same idea. Got it? Wonderful? Okay. Now we need to do a whole bunch of voodoo. Okay? So here's what we've got. We said that V equals V naught plus AT. Now we're going to combine some things. And we said the distance traveled was 1/2 V plus V naught time. Right? Now, here's what I want to do. This is kind of the John Madden thing of physics. Okay? I've got this, right? Can I substitute this around the end of the X, boom, and put that in there for V?
Si, senor.
Yeah.
Left end sweep, right? Comes around the back side, right? Kind of, you know, like little give and go, right? Okay? Little hook, little pitch pattern, right? So I got the 1/2. Now, I'm going to come in here and I'm going to put, now you got to stay with me through the algebra. I'm going to have V naught, right? Okay? I'm going to put this whole thing in here for V. So I'm going to have V naught plus AT plus V naught. Clean that up a little bit. Okay? Still horrible? Okay? And then all that gets multiplied by time. So here's the equation that we just came up with. Came around left end, boom, substitution. Okay? Good? Got it? Grand. Now, we're going to do some serious algebra here. Okay? As opposed to the joking kind. Okay? Serious algebra. Straight face. I'll try and sound like a math teacher. All right, class. We're going to take V naught plus V naught I'm gonna take V naught plus V naught. Abby, what do I get?
No, no.
Yes. Okay.
I blame
V, okay, what's X plus X?
And there he is again.
2X. 1 banana plus 2 bananas, right? Okay? So, okay, back to trying to be simple. V naught plus V naught gets me 2 V naught. So, I have 1/2 2 V naught. Is the AT still there? Yes. Now, this is serious. So, I want to do, wait for it, a double distribution. You going? So, I want to distribute the 1/2. At the exact same time, I want to distribute the T. That's Riley. He's excited. Okay, sorry. Riley. In a very serious tone of voice. What do you get when you distribute the 1/2 and at the same time you distribute T?
V naught T. Plus 1/2 A T squared.
And all that's going to equal the distance, right? Now, okay, beautiful. Now, if you look at the second equation down that you have, okay? If you look at that second equation down, you have, what you have is x equals
The physics teacher's back.
x naught plus vx naught t plus 1/2 ax t squared. Okay? Now, what I did, and this is why I just don't blissfully give you these equations, okay? I do this whole thing so that you can understand where these equations come from. So, this basically says, this is your initial position. So if I'm already 5 meters away and I'm starting the analysis, now, this is going to go, most of the time, this is actually going to be 0. Okay? 95% of the time, you don't have to worry about this. Unless you're starting like on top of a building or Mount Everest and you're going to throw a ball up on top of Mount Everest. Okay, that becomes significant. Most of the time, you're not going to have to worry about this. I will. Huh?
Spring scales,
To measure what?
dry plant material.
The only thing I got measures in newtons. And they're not very... I mean, you can do it. You just divide by 9.8 meters. You just divide by 9.8, and there you have it. And that gets you in kilograms. But they're not real.
What do you think, can biology handle it?
Oh, seriously, get over it. As long as you don't tell them what it means. Yeah, I've got some back there. I've got 2.5s that are back there on the center table. Those would be the biggest stuff you measure. Are these
That's the
like
biology teacher.
California plants or Colorado plants? I know, I see you guys with the grow lights back there. I'm just saying. You know, Super's been in asking me about, wavelengths and light. You're coming in wanting scales. I just put 2 and 2 together here. So,
He never could add right.
I know. This is true. That's why I teach physics and not math. So, they're on that center table there. The 2.5, you're getting warmer. No. Right there in front of you. Nope. Turn a little bit more. You're getting, other way. Other way. Walk towards me.
Oh, your demo thing.
Yes. There should be like a box of 2.5s, 5s, and 10s. Hold on. Stop that for a second.